fantastic. Yeah, welcome to this new week of Frontier Condensed Matter Physics seminar series. And this week, we're actually extremely glad to have Jinguang Cheng to give a talk on his new discovery of this sort of a bulk superconductivity of this nickelate-based superconductor. And since the discovery of this material last year by Meng Wang's group, there are a lot of controversy in terms of whether superconductivity in this compound is actually a bulk or sort of interface superconductivity. I think this new work by Professor Chen really shed new light on this. So for this reason, I actually get him to get up like 3 o'clock in the morning in Beijing to give this frontier condensed matter physics seminar. Yeah, thank you so much. Yeah, you can get going. Yeah.
Okay. So thank you, Professor Dai. Hello, everyone. So my name is Jinguang Cheng. I'm from IOP, Chinese Academy of Sciences. So as we just discussed, I will try to convince you in my talk that we indeed observed the bulk high TC superconductivity in the bilayer nickelate. But this is the rare earth praseodymium doped substituted 327 phase under pressure. This is the outline of my talk. So in this talk, I will maybe spend half of my time, maybe half hour, to give an overview on the recent experimental progresses of the nickelate superconductors. So this is a requirement of Professor Dai. He asked me to spend at least a half hour to give an introduction about this field. So I will talk about the infinite layer nickelate superconductor discovered in 2019, and the bilayer and trilayer nickelate discovered last year and this year. And at the end of this part, I will summarize the current status and some open issues about nickelate superconductors. So as an emerging new field that are developing quite rapidly, I'm sure I cannot cover all of those progresses in this single talk, especially those theoretical proposals and discussions. And for an experimentalist like me, I prefer to focus on the experimental findings that are directly related to superconductivity. In the second part of my talk, I will present our result that we confirmed the bulk high TC superconductivity by observing theory resistivity and diamagnetic signals. And I will try to show you there are two key factors for achieving bulk high TC superconductivity, that you need to have a single phase. There's no integrals between the 327 phase and other Rhodes-Popper phases. And there's negligible oxygen vacancies at the apical O1 side. And if I still have some time, I will discuss the chemical and physical pressures on the pressure-induced thrust transition. Okay. Let me start by a very brief review on the history of superconductivity. As we know, superconductivity is a macroscopic quantum phenomena that has a lot of enduring research interest since its first discovery in 1911 by a company Onis. A superconductor shows theory resistivity and Meissner effect below a critical temperature, which we call TC. And so the superconductor can transport electricity without any dissipation, and can expel the magnetic flux below the transition temperature, and also under certain magnetic field. This will give rise a lot of a broad range of potential applications in different fields, like scientific research, medical care, and transportation, and even industry and energy in different fields. For example, so in our laboratory, we use a lot of superconducting magnet that has been widely used in our laboratory. So you may refer to this review article for the applications. Even though the superconductors have many advantages, they are not widely used today. One of the main obstacles is that the transition temperature is relatively low, usually well below room temperature. Therefore, one of the main research streams is to pursue high TC superconductivity, high TC superconductors, with a dream to achieve room temperature superconductor. From this phase diagram, you can see the TC actually goes up quite slowly in the first 70 years, from about 4 Kelvin to nearly 23 Kelvin. But in the history of superconductivity, at least there's three, you see three change of the trend of TC versus time. So the discovery of the cuprate in 1986 and the discovery of the iron pnictide superconductors in 2008 have changed the trend of TC. So it will shoot up to room temperature if this keeps this trend, but unfortunately, the TC reached the maximum and keeps for decades. And then in 2014, the superhydride superconductors was discovered, and the TC goes up, but all these superhydride can only be stabilized under very high pressure. So at present, the highest TC that can be achieved at a high pressure is the lanthanum hydrogen 10, with TC about 250 to 260 Kelvin, under about 2 megabar pressure, very high pressure. At ambient pressure, the highest TC is still, the record of TC is still held by the cuprate. It's about 135 Kelvin at ambient pressure for the mercury-based cuprate. And the TC can goes up to 164 Kelvin under 30 gigapascal. For the hydride and the metal and the alloy superconductors, basically they can described by the conventional BCAT theory. But for the cuprate and iron pnictides, basically they cannot be described by the conventional BCAT theory. So we call this unconventional high TC superconductors. So when we look at the structure and the phase diagram of the cuprate and the iron pnictide high TC superconductor, we can find similarities, which may offer us some clues for finding more unconventional superconductors. So for example, both family features a quasi two-dimensional square lattice for the copper and iron cations in the square lattice. And the pairing compound has a long-range anti-ferromagnetic order, and the high TC superconductivity appears when you suppress the long-range anti-ferromagnetic order by either Hall or electron doping or by applying pressure. And in the phase diagram, there's many intertwined competing orders, including the pseudo gap, pneumatic order, charge order, stripe order, etc. So this rich the interplay to start the interplay between these phases and superconductivity has been the main major subject in the last decades. And this information are very important to guide us to find new superconductors, especially unconventional superconductors near the anti-ferromagnetic quantum grid point. At present, the macroscopic mechanism of high TC superconductivity remains elusive because the intertwined electronic orders and complicated many-body electronic interactions for these strong current systems. From an experimental point of view, we may solve this mystery or at least provide some clues by discovering more high TC superconducting systems besides cuprate and iron-based high TC superconductors. So this is also one of the main research directions in the community of superconductivity. In this regard, at the nearest neighbor of the copper in the periodic table of elements, the nickel oxide or nickelate has been considered as the most promising analogs candidate to achieve high TC superconductivity. So it was proposed that the nickel 1+ with the in the square planar coordination can be considered a direct analog to the superconducting cuprate. Even though this proposal has been proposal has motivated many experimental investigations since 1999, but the experimental progress experimental breakthrough was not achieved until 20 years later, 2019, as I'll show you below. So before I show the experimental progress, I will first describe the structures of the nickelate. So here, the reduced Rudolph Popper phases with the general chemical formula, this rare earths M+1 nickel N oxygen 2N+2. So this is green, this phase. So actually it has this square planar coordination and the nickel valence close to 1+. They provide this requirement for the proposal. This reduced RP phases can be abated by reducing the corresponding RP phases, this blue one. So here you can see the coordination of nickel changes from the octahedral to the square planar coordination. These phases, RP phases, can be reduced by heating these phases in a flowing oxygen or with some like calcium hydride to remove the apical oxygen. Then you can get this reduced phase. So I think with this basic knowledge, we can move on to describe the recent experimental progress on the nickelate superconductors. So first, I will show the result on the infinite layered nickelate, this 112 phase. So in 2019, Stanford group led by Professor Harold Huang reported the discovery of superconductivity in infinite layered nickelate. This is strontium doped, it's whole doped neodymium nickelate 112 phase. So this 112 phase is abated by top tag reduction of this corresponding perovskite 113 phase. Just to remove the apical oxygen, you can get this infinite layer phase. So for this infinite layer phase, the resistivity measurement and the AC stability confirmed that shows the superconducting transition with TC around 10 Kelvin, the onset around 15 Kelvin, but their resistivity around 9 Kelvin. So both the zero resistivity and the Meissner effect confirmed that this is the bulk superconductivity in the nickelate. So this experimental breakthrough really is really exciting because this proposal was proposed 20 years ago, and finally the nickelate superconductor was discovered in experiment. Later on, superconductivity was also realized in the quintuple layer, this neodymium 6, nickel 5, oxygen 12, the thin film samples. But TC is relatively low, so especially for the TC0, so it's below 1 Kelvin. The onset is okay, it's about 13 Kelvin. Some follow-up studies have established a dome-like superconducting phase as a function of the doping, whole doping. So this phase diagram is similar with the whole doped cuprate with a dome-like superconducting phase. But the highest TC for the nickelate is around 10 to 15 Kelvin. It's much lower than the cuprate. So there's a different series of the rare earths nickelate 112 phase. So we plotted the highest TC for each series. So we plot the highest TC as function of the A-side cations. So this is the neodymium and strontium, the average size. So we found that also the C-axis, we found that the TC actually increase with reducing the C-axis length. So the C-axis length is actually controlled by the size of the A-side cation. So this observation motivated us to try to answer how will the TC change under compression. So if we apply pressure, will the TC continually increase, and what's the limit of the TC? Can we reach higher pressures? So we try to perform a high pressure study. So the first we need to have thin film samples. At that time, 2 or 3 years ago, it's very difficult to grow this single to grow the superconducting infinite layer samples, the superconducting samples. So one of my colleagues, Professor Jinguang Cheng in LP, they can prepare the high quality strontium doped 112 thin films with a pretty high TC. The TC onset about 17 Kelvin and zero temperature about 13 Kelvin. So we have the samples and we can perform the high pressure resistivity measurement. But it turns out it's not very easy to measure the resistivity on these nickelate samples because this infinite layer sample was obtained by reducing the corresponding perovskite phase. The apical oxygen is removed, so it's very fragile and it's not very easy to perform high pressure measurement. Finally, we use the cubic gamma cell. We put the thin film in a liquid pressure medium. I will explain in detail how about this high pressure technique. So finally, we successfully observed the superconducting transition under different pressures. We found that the transition temperature increase with pressure almost linearly with a slope of 1 Kelvin per gigapascal. And we measured up to 12 GPa. The highest TC can reach about 30 Kelvin. But as you can see here, below 4 to 5 GPa, we can still reach zero resistivity. But at high pressures, we can only observe a drop of resistivity, but we cannot reach zero resistivity. So to figure out what's going on here, we performed the TM measurement and XRD after we finished, after we decompress the pressure cell. We take out the sample from the pressure cell. So we found that under pressure, it produces a lot of structure disorders. And this is before compression. This is after compression. There's a lot of structure disorders. But the main phase is still 1 and 2 phase, but it becomes very broad. This blue one is after compression. So it means that this infinite layer nickelate, the superconductivity is very sensitive to the structure. You have to keep the structure perfectly in order to reach zero resistivity. So this may explain the absence of superconductivity in the bulk infinite layer samples. So for the bulk samples, you can see the XRD is actually pretty, the peak is pretty broad. And so far, the superconductivity cannot be found in the bulk samples. Now next, I will move on to the bilayer nickelate, which is also the focus of my talk. For easy of explanation, so here I show the structure and I labeled this site for different for the atoms. So for the lanthanum, there's 2 sides. So the lanthanum 1 is actually is located inside the bilayer, nickel bilayer, and the lanthanum 2 is located between this bilayer. And there's 4 oxygen site. So this O1 we call O1 is located in the inner apical side, and O2 is the outer apical side, and O3 and O4 is actually within the implant, the planar side. So because I will mention frequently this O1 side, so please remember this O1 means this apical, inner apical side, which is important for this bilayer interaction. So actually, this bilayer nickelate 3,2,7 phase is a pretty old compound that has been known since 1980s actually. But at that time, it's very according to the literature, it's not very easy to prepare a single phase sample. So In 1994, according to this paper, actually by Professor John Goodenough's group, probably this is the first. I can find this is the first paper that they reported to prepare the single phase 3 to 7 phase by using the wet chemistry soil method. In this paper they mentioned in this paper they described in very detail how to prepare these samples. So they use the TGA measurement to confirm the oxygen content. So if you center the sample at in air, so it's a slightly oxygen deficiency. Delta is about 0.08. And in the resistivity, it shows a density wave-like transition around 140 Kelvin. But if you treat the sample under high oxygen pressure, the oxygen vacancy can be removed, and the sample tends to change to a metallic without clear transitions. But if you create more oxygen vacancies, it becomes insulator. So this sample, the transport property is very sensitive to the oxygen content, according to the earlier papers. The single crystal of this Ralston Popper nickelate, so this for this species is can be grown with the optical image floating zone method under different oxygen pressure. According to this paper, so you can get different phases, at different oxygen pressure. The 3 to 7 phase can only be stabilized in a very narrow oxygen pressure range from 10 to 18 bar oxygen pressure. And the major phase is 3 to 7. But if you look at the XRD pattern, actually it's coexistence with the 214 and 3, 4, 10 phases. So actually it's not a real single phase, according to this paper. And until last year, Professor Meng Wang's group in China, they synthesized this 3 to 7 single crystal by using the floating zone method under oxygen pressure about 15 bar. And they grow the single crystal. It looks pretty good. And the resistivity shows a metallic behavior with two transitions. One is around 153 Kelvin, another at 110 Kelvin. This is the susceptibility, minus susceptibility. Previous high pressure, there are some old papers reported high pressure study on the polycrystal 3 to 7 phase. So I can find these two papers. One, they use at the lower pressure, they can use the piston cylinder cell with liquid pressure medium. They found that the density wave transition can be suppressed by pressure. So this decrease about 10 Kelvin per gigapascal. But the previous measurement is only limited to 2 GPa for the piston cylinder. And they also use the diamagnetic cell to measure the resistivity at higher pressures. But here they use the solid pressure medium. They use the sodium chloride as pressure medium. And as you see, the resistivity shows the semiconducting like behavior, not metallic at all. And they measured up to 18 gigapascal, and there's no any signature of superconductivity in the earlier studies. But the story changes until last year. So Meng Wang's group, they grew the single crystal, and then they performed the high pressure resistivity measurement by using diamagnetic cell. They use solid pressure medium, including the cubic boron nitride and potassium boron, these two different solid pressure medium. So they found that above pressures about 14 gigapascal, they can observe some clear resistivity drop. And depending on the pressure medium, this drop can be quite sharp. And this drop can also be suppressed by applying magnetic field. And in addition, they also observed some anomaly in the magnetic stability. This is the original data. So after subtracting this background, they can clearly observe this drop. And so this indicated that there are some signatures of superconductivity, especially the TC onset. The onset of the transition temperature is around 80 Kelvin. So even though the zero resistivity was not achieved in this report, but it's pretty exciting that there's high TC superconductivity in the bilayer nickelate under high pressures. In addition, there's a pressure-induced structure change from this ambient pressure phase AMM symmetry to a high pressure FMM symmetry. So the change of the structure is mainly about the nickel oxygen nickel bond angle. So it changed from 168 degree to about 180. This bond angle is become straight in this high pressure phase, and it looks like the high TC superconducting phase is directly related with the high pressure phase. But in this original in this first report, no zero resistivity was achieved. Later on, Professor Huiqiu Yuan's group from Zhejiang University, they also performed the resistivity measurement on the single crystal samples from Wang's group. But here they use diamond cell, but they use the liquid pressure medium, and they measured 7 samples, and in 4 samples they can observe zero resistivity, and one of the key factors to achieve zero resistivity is to measure tiny samples, about 10 to 100 micron, and use the liquid pressure medium. So this indicates that the sample is not very homogeneous. So you have to pick up a very small sample, and the sample maybe in the small region is homogeneous. And the TC onset, the transition is quite sharp. The onset about 66 Kelvin, and the zero resistive temperature can reach 40 Kelvin at 20 GPa. So this is, I think this first signature of superconductivity, zero resistivity is achieved. But in this paper, no Meissner effect was reported. It seems to be very difficult. I think Huiqiu Yuan's group also tried to measure AC stability, but it seems to be quite difficult to detect the diamond signal, especially under such high pressures by using diamond cell. So this is the result from Li Ling Sun's group. They use this modulated AC stability technique. So basically, this technique is more sensitive than the conventional mutual induction method. So they use a reference vanadium, which is also a superconductor under pressure. So by comparing the signal of this transition, they can estimate the superconducting volume fraction of the nickelate superconductors. So they found that the superconducting volume fraction is on the order of 1%. So it's quite a small superconducting volume fraction. So it suggests it's a filamentary superconductivity. And according to this recent update, they propose that the filamentary superconductivity actually comes from the interface between the 327 and the 4310 phases. It's not bulk, it's high TC superconductivity. So that's why there's still under debate whether we can achieve bulk superconductivity or not in this 327 phase. Actually, my group has participated in the high pressure studies on the 327 phase in collaboration with Wang's group. So we are probably the first few groups that became aware of the sample dependent behaviors in these 327 crystals. So we actually we measured 3 samples from Wang's group with different high pressure technique, including diamond cell, cubic cell. And we also tried the solid pressure medium and liquid pressure medium. We found the behavior, we can indeed every time we can observe some resistivity drop, but the behavior change is changed from sample to sample, and also it's very sensitive to the pressure medium. So only in the liquid pressure medium we can observe a sharp transition, and in one sample we can achieve zero resistivity, but it's quite broad. And So this is earlier studies on the single crystals. And for these single crystals, when we finish for these 3 samples, after we finish the high pressure resistivity measurement, we measured the SEM and energy dispersive spectroscopy. We found that there's some chemical inhomogeneity. So this green color is for the nickel. So in some regions, we found there are some nickel-rich regions, and so this is in a very small, like a micron size. So we confirmed that the crystal has not a very high quality, so there's some chemical inhomogeneity. Actually, according to this most recent paper published in Nature, actually one of my colleagues, Chen Zheng, they developed the energy filtered multi-slice electron tachography, this MEP technique. So it's difficult. I'm not familiar with this one, but we just mentioned this is MEP technique. It's a very advanced STM technique, so they can directly image the oxygen vacancy. So by using this technique, they found that they also measured the 327 crystal from one's group. They found that the oxygen vacancy mainly located at the inner apical O1 side. So this O1 side. There's a large the oxygen content change from at different regions. It changed a lot. So some regions it's very close to the stoichiometry, but there's some regions so it's far from the stoichiometry. So you can see this oxygen content also shows significant inhomogeneity. So both the chemical, both the cations and also the oxygen content shows a large, strong inhomogeneity for these single crystals. In addition to this conventional, those we call the bilayer phase, this 2-2-2 phase, so bilayer phase, actually 3 groups independently reported. Actually, there's another competing phase, polymorph 1-3 phase. This phase consists of the alternative growth of the single layer, monolayer, and the trilayer. So this is 1-3 phase. And for this 1-3 phase, high pressure resistivity measurement also shows the appearance of resistivity drop around 80 Kelvin. So, but also there's no zero resistivity. So then so this raises a very serious question. So the high TC susceptibility comes from this bilayer phase or from this 1-3 phase. So this is in addition, there's no the superconducting volume fraction is quite low. So there's why there's a lot of controversies. So there's a lot of debate about the nature of this superconductivity. Moreover, actually, by using the flux method, Junjie Zhang from Shandong University in China, they can also design a hybrid nickelate, this 1-2-1-2 phase. So basically, they just combine this monolayer and the bilayer phase. They create this hybrid nickelate. This is the single crystal. It's not very big, but the quality looks okay. Okay. So to complete my introduction, so let me also briefly summarize the high pressure result on the trilayer nickelate. So only a few slides. So actually last year, the signature of superconductivity has been reported in the pressurized this 4-3-10 phase. So there are 3 independent reports. This is 2 about the started on the polycrystal and this work on the single crystal. So basically, they can observe the resistivity drop on below 20 Kelvin under pressures about 40 to under pressures above 30 gigapascal. But the zero resistivity was not achieved in these studies. But in these studies, the resistivity can drop about 95%. But until we know, until very recently, Junzhao's group from Shanghai, from Fudan University, they not only observed the zero resistivity, but also provided the result of the Meissner effect. So they confirmed a bulk superconductivity in these 4-3-10 phases in the single crystal. This is the phase diagram, and the superconducting volume fraction can be as large as 80%. But for this trilayer sample, the highest TC is about the onset is about 30 Kelvin, and zero resistive temperature is about 12 Kelvin. So it's the onset is temperature is much lower than the bilayer phase. Also, this also undergoes a structural transition and pressure. So let me summarize the current status of the nickelate superconductors. So basically, the discovery of superconductivity in both in infinite layer, the nickelate, bilayer, and trilayer nickelate marked the coming of the nickel age of high TC superconductivity. I think after the copper age and iron age. For the infinite layer nickelate, bulk superconductivity with TC around 9 to 18 Kelvin has been established in the thin film samples, but superconductivity cannot be achieved in the bulk form so far. And its highest TC is the onset temperature increase linearly with pressure and can reach about 30 Kelvin at 12 GPa. For the trilayer nickelate, bulk superconductivity has been established under pressure with the TC onset about 30 Kelvin at pressures over 30 gigapascal. For the bilayer nickelate, signatures of high TC superconductivity with TC onset of 80 Kelvin was reported in the pressurized single crystal, and zero resistivity up to 40 Kelvin has been observed, but the tiny diamagnetic signal indicated a filamentary nature for the observed superconductivity. So the main problem is the quality of the single crystal is still relatively poor at this moment because the presence of competing Rodden's Popper phases and maybe some 1,3,1,3 phases, and also the oxygen vacancy. So there are many open issues regarding the high TC superconductivity for the 3-7 phase. One is the origin of the high TC superconductivity, and whether it's from the bilayer phase or from the 1,3,1,3 phase. Is it bulk or filamentary or from the interface? And is it possible to realize bulk high TC superconductivity by control the phase purity and oxygen content? And what's the role of the structure transition? And is it possible finally to realize high TC superconductivity at reduced at lower pressure or even ambient pressure? So to resolve these issues, so the important thing is we need a high quality single phase samples, not to mention single crystal. We need a single phase 3-7 phase samples. And also, as I mentioned, the transport property is very sensitive to the pressure environment. So we need to measure the physical properties under hydrostatic pressures up to 20 GPa. So to address these issues, so because we at the beginning we started a single crystal, but we found it's pretty difficult to figure out what's going on because of sample quality issues. So we tend to the polycrystal samples, and we use the large volume multi-envelope press. So in the second part, I will present our result. So basically, we follow this the similar procedure and this paper. So we prepare the polycrystal samples with the soil gel method. So we prepare the praseodymium doped lanthanum 3-7 phases. So the content of PR can change from 0 to 1. So it's about 1/3 substitute lanthanum. We try to higher content, but above 1.5, then the impurity phases, impurity like 214 phases will appear. So after prepare these polycrystal samples, we perform the basic characterizations, including the XRD So the SRD confirmed is single phase and it has a rhombic structure. And this is magnetic stability and resistivity. Basically, the resistivity increase and also the magnetic stability also increase with increasing doping. This is understandable because praseodymium has a magnetic moment and also the resistivity increase and the density view transition becomes very weak up to 1/3 doping. But this polycrystalline sample is pretty homogeneous. So according to this FCMP and EDS measurement, we confirmed the uniform distribution of the cations, and the cation ratio is very close to the expected chemical stoichiometry. For example, for this lanthanum 2 praseodymium nickel, the ratio is 2 to 1 to 2. So it's very close to the starting ratio. So then we have the polycrystalline samples. We are ready to measure the transport, especially resistivity and high pressure. So before I show the result, let me first explain the high pressure techniques we used in our study. We used large volume, multi-angle, high pressure approach. So not the diamond angle cell, we use a pair of diamond. So it's a uniaxial compression. But here we use the multi-angle high pressure techniques. So one is a cubic angle cell. So here it consists of 6 angles compressing the sample from 3 orthogonal direction. So, and if the 2-stage multi-angle or 6/8 multi-angle, it uses 8 angles actually to compress the central orthohedral pressure medium. So the measured sample is actually put inside a Teflon capsule. This is a Teflon capsule filled with liquid pressure medium. So the sample is surrounded by the liquid pressure medium. So such a multi-angle geometry and the liquid pressure medium can ensure very good hydrostaticity, or at least isotropic compression. So the cubic angle cell can reach pressure about 15 gigapascal, and the multi-angle can reach about 20 gigapascal. And for both techniques, the sample space is pretty large. So the inner diameter is about 1 millimeter, and the depth, the length of the Teflon capsule is about 1.8 millimeter. So it's at least 2 or 3 orders bigger space than the diamond angle cell. So in comparison for the diamond angle cell, so the sample space is very tiny. Normally the hole size is around 100 micrometer, and the depth of this hole is about 50 to 60 or even smaller, even smaller micrometer. So, and actually for most research groups using diamond angle cell, they normally use the liquid, solid pressure medium, such as sodium chloride or potassium borate for the transport measurement. So this will produce a strong non-hydrostatic pressure conditions with uniaxial pressure and some shear stress or strain. So this will influence the transport property significantly. So to illustrate such kind of non-hydrostatic pressure, I found some pictures from this paper. So in this paper, they put a chromium metal inside a diamond angle cell. They use 2 different pressure medium. One is a mixture of methanol, ethanol. Another is silicon oil. Both are liquid, but methanol ethanol mixture has a better hydrostaticity than the silicon oil. As you can see, under high pressures, the sample deformed significantly in the silicon oil because silicon oil will solidify under high pressures. So, okay, I show our result. First on the polycrystal 327 phases undoped sample. So we just measure resistivity as a function of temperature under different pressures by using the cubic angle cell, this is piston cylinder cell under lower pressure, and a multi-angle. So we measured 2 samples. This is measured in ROP, and this measured in ISSP, University of Tokyo. So basically, the result is quite reproducible. So we found that we started to observe a resistivity drop around 7 gigapascal, and then this drop becomes stronger And at 9 gigapascal, we can reach zero resistivity. And the superconducting transition moves to higher temperatures with increasing pressure. And up to, we measured the highest pressure about 18 gigapascal. The zero resistivity temperature, TC0, can reach about 40 Kelvin here. And the onset temperature is about 78 Kelvin. And in normal state, it shows this kind of linear in temperature behavior, like it's called strange metal behavior. So based on this resistivity result, we can construct this phase diagram. So basically, the pressure suppresses this density wave transition, and the superconductivity appears above 6 gigapascal. But the zero resist temperature, it appears at much higher. TC0 appears at much higher pressures. So basically, in the polycrystal samples, we can reach zero resistivity easily, and it's very reproducible. So this the good point. This is one advantage of the polycrystal sample. It's uniform. And in comparison, in the literature, there's some result, resistivity measured with diamond cell and solid pressure medium. As you can see, there's only 30 or 5% drop of resistivity. But in the liquid pressure medium, we can reach zero resistivity very nicely. So this demonstrates the difference between the hydrostatic pressure versus non-hydrostatic pressure. Okay, then we measured the praseodymium doped 327 polycrystal sample. So basically, the measurement is similar. It's quite simple. So we measured two samples with cubic envelope cell and multi-envelope cell. So the result is very reproducible. So for this doped sample, we start to observe the resistivity drop around 8 GPa, and we reach zero resistivity around 12 GPa, and the transition also moves up. So finally, at actually above 18 GPa, the transition almost doesn't change much, almost saturated. So there's an enlarged figure here. You can see at about 18 gigapascal, the TC0 can reach about 60 Kelvin. So this is the highest value for the nickelate superconductors reported so far. So even though the praseodymium doped sample shows a higher resistivity at ambient pressure, but it shows a better superconducting transition temperature in terms of the TC0. So we are very curious about this observation. So after observe the zero resistivity, then the next issue is how about the superconducting volume fraction? So here we use the AC magnetic stability to estimate the superconducting volume fraction. So it's very simple. It's just we make two coils, we put the sample and a reference put it in this coil. When the sample becomes superconducting, the repulsion of the magnetic flux will produce a drop in the magnetic stability. So by comparing the drop of the magnetic stability between the reference and the sample, so we can estimate the superconducting volume fraction. For example, here we measure this sample, we put this sample and a lead in a coil. So this is the transition from the lead. For type 1 superconductor, it shows a very sharp transition, and this doesn't, the TC will decrease with increasing pressure, but this drop doesn't change, so it keeps the same. But when this sample becomes superconducting, you will observe an additional drop. Normally, it's quite broad because it's type 2 superconductor, and by comparing this magnitude of this drop, so we can estimate the superconducting volume fraction. Actually, it's not the real Meissner effect. It's the superconducting shielding volume fraction. So basically, we use this method for our high pressure studies. Is quite for different studies. So this works very well to estimate the superconducting shielding volume fraction. So we performed the AC stability measurement on these two samples in the cubic envelope cell. So for this undoped sample, we measured up to 15 GPa. we only observe the transition from the light. There's no any signature of the transition from sample. But to our surprise, for this doped sample at 15 gigapascal, in addition to the transition of light, we observe this very broad drop from this decrease of the susceptibility, starting from 75 Kelvin. So by comparing this drop and of the sample and the light, so it has a volume fraction about 6% at 15 gigapascal. So this is quite encouraging. So how about at high pressures? Then we measure the resistivity with the multi-angle in Japan, in IIS Institute for Solid-State Physics, University of Tokyo. So this is the setup. So they use a closed circle refrigerator to cool down the large cell. But at that moment, the lowest temperature is about 8 Kelvin. So we cannot use lead as a reference because the transition of lead is below 7 Kelvin. Then we choose iron selenium as a reference because in our previous studies, we are very familiar with the transition of the iron selenium. It's a superconductor at ambient pressure with TC around 9 Kelvin. And under high pressure, the TC will goes up, and the highest TC are around 38 Kelvin at 7 GPa. So we first check this single iron selenium. We put the iron selenium and lead in the coil. We measured at ambient pressure and at high pressures. So the iron selenium will undergo the structural transition from the layered structure to a three-dimensional structure above 10 GPa. And above 10 GPa is non-superconducting. So indeed, as you can see here, at low pressure, we observe the transition from the iron selenium and also the lead. And at 12 GPa, so only the transition, we only observe the transition from lead. The iron selenium becomes non-superconducting. So we can safely use iron selenium as a reference. So basically, we put the iron selenium and the praseodymium doped sample in the coil and measure the AC stability. So you can see at lower pressures, we only observe the transition from the iron selenium. And the transition temperature, about 30 Kelvin, is consistent with our previous study. At about 15 to 16 gigapascal, you see the transition from iron selenium disappear, but we observe some drop, some kind of decrease anomaly at high temperatures, and this becomes clear with increasing pressure. You can see at 20 GPa, it shows a very clear change of this AC stability. And we measure two samples. The second sample shows much better the data quality because we change the excitation current and also the frequency. So the data quality becomes much better after the first measurement. We have more experience. So we can estimate the superconducting volume fraction by comparing this drop, this magnitude of the signal, this superconducting signal. So assume that iron selenium has 100% superconducting volume fraction at 9 GPa. So we just make a simple calculation. So we can calculate the superconducting volume fraction for sample 1 and sample 2. For this sample, at 20 GPa, it can reach about 57%. But this is at about 8 Kelvin. You see this is still decreasing quite rapidly. So at the lowest temperature, the volume fraction to be higher. For the second sample, it's much better. So the volume fraction can reach nearly 100%. But I want to mention that this is just a rough estimation because iron selenium, we are not quite sure it's 100% or not for these peculiar samples. But at least this result, we are quite confident that has a very large volume fraction for the superconductivity. It should be above high TC superconductivity. So basically, we observe zero resistivity and diamagnetic signal. So these two characteristics for the superconductivity in the praseodymium doped sample. And it seems that the superconductivity is much better than the undoped sample. So why the doped sample is better? And if we can figure out the reasons, probably we can design better bulk high TC superconductors. So in the following, I will show you some of our characterizations. So we measured the neutron diffraction at Oak Ridge National Laboratory. So for these two samples, we found that for the undoped sample, especially for this 0010, this reflection, so the peak is quite broad. It shows a symmetric Warren-like shape, indicating that there's some shorter range order along the c-axis. But in contrast, for the doped sample, it shows a very sharp transition. So this indicated that it has a much better quality, sample quality. And from the refine, we also refined the oxygen occupancy of the O1 site. We found indeed for this undoped sample, there's some vacancy. But for this doped sample, it's nearly fully occupied. So from this neutron diffraction, we indeed show that the doped sample has a better quality and negligible oxygen vacancy. And we also used the TM to further confirm this result. For this undoped sample, for this 327 polycrystal, in most regions it shows a bilayer phase, but this 327 phase. But we frequently observe this intergrowth of this 327 and bilayer, trilayer, and bilayer, trilayer. This intergrowth, and also there's 214 phase. It's very easy to observe this intergrowth. But for this praseodymium doped sample, there's no trilayer phase. We measured several samples, and this is we confirmed there's no trilayer phase. Only a few the monolayer intercalated between this bilayer phase. So this further confirms that this doped sample has a much better quality without this intergrowth. But you know the TM is still a local probe, so we also use the NQR as a bulk probe because we measured 0.5 gram polycrystalline samples. So this is for the undoped sample. We observed this very complicated structure. So I think I will skip the details for this. Basically, lanthanum. This is lanthanum NQR. It has a nuclear spin 7.5. So we should have 3 sets of peaks. This is okay. But for each set, we found that the peak actually split to 4 peaks. So there's 4 peaks for each set. This indicated that there's 4 distinct lanthanum site, lanthanum 2 site. So based on the TM result, we proposed such kind of structure model. So there's the intergrowth between this bilayer and trilayer. So if you look at the lanthanum 2 side, so this intergrowth will create 4 distinct lanthanum 2 side. So in addition to this lanthanum 2 at bilayer and trilayer, so there at the interface, you will create this 2 side, and they should located in between these 2. So from the frequency and also we found also this should have the same area. So from the fitting of this peak, we found they have the similar area. So this further confirms this picture. In comparison to this undoped sample, for this, we also measured the NQR of the trilayer single crystal. Indeed, for this peak on the left side, they have the same frequency. So this confirms that indeed in the 327 phase, there's some trilayer phase. But for the praseodymium doped sample, we only observe a very broad peak for this 327 phase, and there's a side peak around this side. But definitely there's no trilayer phase, and also the intergrowth with this phase. So from this result, we can basically confirm the bulk high TC superconductivity is indeed come from the bilayer 327 phase. And we also, in collaboration with Dr. Ke Jinzhou from Diamond Light Source, he used the XAS to confirm the PR ions has a trivalent state, because we know the the valence can change from 3+ to 4+. Here is 3+. And we also use the TGA to further confirm that there's negligible oxygen deficiency. So the delta is very, very small. So, and also with collaboration with Chen Zheng in LOP, he uses the MEP technique to confirm that for this PR doped sample, so the inner apical O1 site is almost oxygen fully occupied. So the oxygen vacancy is very small. And by using the EOS mapping, he also confirmed that the praseodymium primarily located at the lanthanum 2 site. It means between the bilayer. So basically, this above result, we confirm that the praseodymium doped sample has a nearly pure bilayer structure with negligible oxygen vacancy at the O1 site. And then in this sample, we achieved the bulk high TC superconductivity with the transition temperature, especially TC0 around 60 Kelvin, which is so far the highest value among the nickelate superconductors. Okay, I think at this point, basically, I answered the first 2 questions. The high TC superconductivity is from the bilayer phase, and you can achieve bulk superconductivity by control the phase purity and oxygen content. And then in the following, I will quickly go through these 2 parts about the structural transition. So basically, we prepared a series of these rare earth doped polycrystal samples. So we started the structure at ambient pressure by using the neutron diffraction. So basically, with reducing the size of the rare earth, the lattice parameter and the volume decrease, and also the nickel oxygen bond length and nickel oxygen or nickel bond angle also decrease. This means this is understandable because when you change reduce the size of the A-side cations, the structural distortion becomes stronger. So orthorhombic distortion becomes stronger. Then we performed high pressure XRD for each sample, and we observed the structural transition. You can see this peak splitting in the orthorhombic structure is merged together in the high pressure tetragonal phase. So for the undoped sample, the structural transition occurs at about 6 to 7 GPa, which is very close to the pressure where we observe the resistivity drop. And this critical pressure, PC, this is about half of the single crystal, which takes place at 14 GPa. And for this PR doped sample, the structure transition takes place at 11 GPa, and which is about 4 to 5 GPa higher than the undoped sample. Basically, we performed the high pressure XRD on each sample, and we determined the transition pressure for the structure transition, the PC for the structure transition. And we found that the critical pressure for the structure transition increase with reducing the A-side cations. And we also did the calculation, and the result is also similar. When you reduce the size of the A-side rare earth cations, the transition pressure increase very quickly. And from a linear extrapolation, we can get a critical size for the A-side cation at about 1.23 astron. So actually, we need a larger A-side cations in order to reduce the PC to ambient pressure. So not to replace lanthanum with smaller cations, but bigger, larger cations, such as strontium and barium. Maybe it's possible, but so far there's some report about the strontium doped samples. This is one paper on the polycrystal samples. They can substitute lanthanum with strontium up to 0.1. So this is quite low, only 3% substitution, and it remains metallic and no superconductivity. And in this report, there's no structure study. And in this report, I think from Wei Xie's group in Rutgers or Michigan. She synthesized strontium doped bilayer nickelate. So in this paper, they use high pressure, high temperature synthesis. They can increase the strontium content to 0.2, around 0.2. But for this sample, they found under high pressure, the resistivity first decrease and then increase. And there's no superconductivity up to at least 27 gigapascal. Okay, I think I will summarize my talk. So I think I will not read this summary. Basically, I already explained all of this result. And there's a lot of collaborators actually involved in this study. Here, especially thanks to my postdoc, Ningning Wang, and my PhD student, Wang Gang. They synthesized these polycrystal samples and performed this high pressure measurement. And the multi-angle measurement and high pressure were performed by Xiaoling Shen and Professor Yoshida Wataku in University of Tokyo. And there's a lot of collaborators. The NQR was performed by Zhou Rui in LOP and STM, some by Huixin Yang, and some by Chen Zhen in LOP. Okay. And before I conclude my talk, I would like to take this opportunity to make advertise about our new facility called CCAF, Synergetic Extreme Condition User Facility. So we are aiming to build a world-class user facility with multiple extreme conditions. Basically, we combine the high pressure, low temperature, and strong magnetic field, and all kinds of many different kinds of measurement techniques in this one facility. So we try to provide a one-stop service for experimental condensed matter physics and material sciences. So this facility is open for users from both domestic and also foreign users. So you can find the information on this website. There's a total of 20 experimental stations in our facility. And I'm in charge of one of the station is a cubic envelope cell or high pressure station. So here we have two. This is for the high pressure. We can reach 15 GPa. Then we integrate the cubic envelope cell with traditional this helium-4 cross-stat, and we also have a dilution refrigerator with a superconducting magnet, so we can reach down to 50 millikelvin and 12 Tesla under a high pressure of 15 gigapascal by using this technique. And recently, in collaboration with Professor Guanghan Cao, in our cubic envelope cell high pressure station, we found superconductivity in this chromium-based Kagome metal, this 135 phase. So around 4 GPa near the magnetic quantum point, we observed superconductivity. With that, I think I will conclude my talk, and thank you for your attention.
Thank you. Thank you, Jinguang. Very nice talk. Any question for him?
Benji, I have a question.
Yeah, Chima. Yeah, go ahead.
So Jinguang, I just was wondering, for the ambient pressure, are the properties roughly this praseodymium doped one are the properties roughly the same as the usual case, the undoped case?
Actually, the resistivity increase by 1 order of magnitude. Let me show you. So here is the resistivity at ambient pressure. So the red one is the undoped sample. With increasing the doping, the resistivity actually increase. For this presbyterium doped sample, it shows a semiconducting behavior.
What about the phase transition? I think it's like 100 something Kelvin.
From the resistivity, it's not very clear. It's hard to define the transition. It's not like for the undoped sample, there is a clear kink.
But you also have more disorder, right? In the pristine dope sample, I mean, it's clearly more disorder.
No, there's disorder. You mean the intergrowth? The intergrowth is
No,
there's less.
not intergrowth, but it's just the size differences between pristine and lanthanum,
Yes.
right? And you can scatter electrons, right?
Yeah, but fortunately, the praseodymium goes to the lanthanum 2 side.
Ah, okay.
Yeah, it's between the bilayer.
Okay.
So at this point, whether this 100 something Kelvin transition still exists here.
Yeah, he clearly sees it. Yeah.
No, sorry. Where?
You mean at ambient pressure, right?
Yeah.
So we didn't from the susceptibility. It's difficult to define because the praseodymium has a strong magnetic moment, has a large magnetic moment.
Right.
Yeah.
Okay. Yeah. Thank you.
Yeah, any other question for Jinguang? So I guess basically, I mean, what you find is that the structural distortion. I mean, are you claiming that basically the oxygen intersite fully filled is actually better for high TC? Is that the story? The takeaway message?
Pardon me?
Your oxygen one site, you said in the pristine dope sample, oxygen one site vacancy is actually less, right? Do I take it as
Yes.
you're suggesting that typically people thought to remove apical oxygen is good for high TC, right? You're saying that in this case that have filled oxygen one site in the pristine dope sample is actually better for TC. Is that?
Yes. So there's 2 factors. One is O1 site vacancy. There's almost no vacancy at O1 site.
Right.
And secondly, there's no intergrowth.
I see.
But for the undoped sample, there's a large portion of the intergrowth especially from the NQR measurement. So we found there's.
I see.
Yeah. Somehow the substitution of the praseodymium can suppress the intergrowth, especially can suppress the trilayer phase.
So then you think the intergrowth is not the reason for high TC. I mean, it should be the pure.
So it's because we didn't observe this intergrowth for this doped sample.
Right. But the dope sample has a fully occupied the O1 site.
Yes.
Which is different from the original hypothesis, right? The theoretical hypothesis, you need to remove it for high TC, right? But here you're saying you don't need to remove it.
No, I think according to some theoretical proposal, O1 should be important.
Okay.
Yeah, because the DZ square orbital between this in the bilayer, you need the O1 oxygen to bridge this interaction.
I see.
Yeah. Yeah, I think this I don't know. Maybe these two factors are correlated. So because we have no intergrowth and therefore we have no oxygen vacancy at O1 side.
Okay.
So I have a strong belief they are correlated with each other.
Okay.
Because the 327 single crystal actually grows the crystal under oxygen pressure. So why still it has a oxygen vacancy, and also there's a different competing phases. So I don't know. I still have some.
Yeah, I understand. Yeah. Okay. Any other question for Dr. Chen from the audience? Okay. I mean, the talk seemed to be very clear. If not, yeah. Thank you very much. Yeah, thanks for getting up again. Such late time.
Thank you.
Yeah, attendance is great. Yeah. Thank you.
Yeah, thank you. Thank you all.
Yeah. Bye.
Okay, bye.